So virtual work. So we did trusses last week. This is an important section, so we're going to spend this week and next week on it. So we didn't have a video lecture because I would figure we'd just do a kind of a condensed version this week, and then we would do kind of the same thing next week. So I'm going to focus specifically on beams today, and we're going to focus on frames next week. Okay, but we're still building off the ideas of virtual work that we established in the truss section. So you'll see that we'll essentially just take the same formula and repurpose it to use for beams. Okay, so objectives today is to first understand the strain energy that's created by bending. Okay, so we defined strain energy before in the context of trusses as strain energy due to elongation and compression, but now beams undergo different types of deformations, right? So they bend, they flex, so we have to define strain energy for that. Then we'll apply virtual work using that definition, right, to beams undergoing bending. And very importantly, okay, I need you to fuse this into your brain. We're going to ignore deflections, deformation due to shear. Okay, remember we said beams undergo both shearing and bending, right? But for the purposes of virtual work, we're going to ignore shear, and I'll talk about why that is. Okay, so again, same thing here, assumptions, right? I always emphasize assumptions, and I'm trying to be upfront about the assumptions here, right? What assumptions are we doing, or are we making when we carry out principle of virtual work for beams? Okay, well, for typical beams, the deformations, according to the book, the deformations caused by shear are some percent of flexural deformations. Can you guys guess what that percent might be? So the flexural deformations are those caused by moments. So we're saying, okay, if I shear a beam, I'm going to get a certain amount of deflections. If I bend the beam, I'm going to get a certain amount of deformation. What percentage do you think is typical? Okay, so Logan thinks 70%. Any other guesses? Brett thinks 5%. Okay, warmer. Come on, you guys just have to put numbers in there. All right, 15, 1, 2, 15, 2.5, 0.1, 20, 37. Good, okay, I like it. So it's got to be a small percent, right? Because we're going to ignore them. So in fact, they are less than 1%. So whoever wrote less than 1% is right. Less than 1% of flexural deformation, so very small, okay? And when we say typical beam, we mean like typically a slender beam, okay? So the overall effect is that we ignore shear deformations. Right? So that's our key assumption here. So we're going to only focus on virtual work due to bending. Okay, there are a few exceptions though, and these are the ones that you need to keep in mind, where shear may be significant, right? So these would be non-typical beams. So one exception is the beam is deep. Does anybody know what a deep beam is, or what I mean when I say a deep beam? It's like really far underwater, right? Okay, Jeff's saying long web. Okay, good. Yeah, pretty much. Yeah, so a deep beam, if I can draw it, would be a beam that's kind of like this. It's like very, very fat, right? So the depth of the beam, which would be the length of the web, like Jeff said, I mean the width, technically the width of the whole, the depth of the whole beam, but depth. So the height of the beam versus the span of the beam. Okay, so the ratio of depth to span is smaller than for a typical beam, right? So for it to be considered deep, the span over depth would be somewhere under 3, okay? A slender beam, which I brought up over here, would be the opposite of a deep beam. It would be very long and short, okay? So when you have deep beams, shear deformations can have a bigger role than bending, right? Because a deep beam is not going to bend very much at all, right? So that's the idea. Another thing might be if the web is thin, right? So if I'm now looking down the beam at the cross section, the web, that part in the middle, right? If that's very thin, then that's going to deform more in shear. Remember, I think we talked about this before, is that very similar to trusses, right? We talked about trusses, how the diagonals actually take shear and then the chords actually take bending. It's very similar in a beam. Actually, it's identical in a beam. The web, the diagonals in a sense, they take the shear, and the flanges at the top, they take the bending. So web resists shear, flanges resist flexure, bending. Okay? So if the web is really thin, then maybe that might actually deform more than, or deform significantly. Okay, and very finally, if the shear modulus is low, this is usually denoted as a J. That would mean that possibly significant deflection is due to shear. All right? But in general, it's highly unusual to see deep beams or thin webs or low shear modulus. So for typical materials, typical beams, these are certainly exceptions. Okay. So just keep that in mind, though. Don't go design a bridge after you graduate and forget to consider shear deflections, and then blame it on me. Okay. So I'm just covering my bases here. I assume no liability. All right. So now we've ignored shear out of our minds, so we'll focus on bending now. So who can restate the principle of virtual work in the most general terms possible, not related to trusses, just in the most general terms possible? It's an equation, right? Anybody want to take over my screen and annotate? So Logan is saying external work equal to internal work. That's a very good definition. I like it. So let's go with that. I'm just going to just fill in virtual here, but the idea is sound. Okay. External virtual work potentially is equal to internal virtual work. Okay. And I'm going to add one bit of detail here where we define internal virtual work as virtual what? You guys remember? We had another term for internal work. Okay, strain energy, right? So internal work is due to the internal strains that are developed in our structure as it's deforming. Okay, so I'm putting virtual here in parentheses because you can remove it and you still have a valid equation. It's just not the virtual work equation. It's just conservation of energy, right? But so if we include the virtual there, then it's virtual work. And this 3 lines means defined as. Okay. So we're going to start from here. All right. For trusses, we had to define strain energy in a particular way. For beams, we're going to define strain energy in a different way to account for the bending. Okay. But let's start with external work first, because that's the easier part. So external work is defined essentially the same way as we did for trusses. So for an applied load, oops, geez, there we go. Right, for an applied load, my beam's going to deflect like that. So I'm going to get a external delta here. So using the same notation. And so my external work is going to equal to my P times my delta. Okay. So that's very similar to trusses. Okay. But for beams, we also have to account for potentially external moments being applied to the structure, right? So we need a definition of work for moments as well. And so if I apply a moment here, it's going to cause a similar rotation there at the end. Right, so it's going to cause the end of my beam to rotate. And so my external work due to applied moment externally is my moment times my angle. Okay, notice that these are in the same units, right? So that's a good way to remember. Force times displacement, moment times angle, we both get force times distance, right? Easy enough. So Kobe is asking 2 different ways to do the same thing. You can think about it that way, yeah. Well, let's think about it. No, they're not the same thing. Okay, why are they not the same thing? Can anybody explain why applying a load and an end load and an end moment is not exactly the same thing?
Could it possibly be that the moment causes a reaction at the other ends, or maybe because it causes a different type of shear? Maybe I'm tripping.
No, so that's the second thing you said, I think is very, very correct. So they will both cause reactions, but they won't cause the same type of reaction. I get both things are right. They won't cause the same type of reaction, right? So the moment will be counteracted by another moment there at the end, but it actually won't generate any shear in the beam at all. Whereas the force will generate both moments and shear in the beam, right? So if you think about the moment diagrams for these 2 cases, if I do the moment diagram for the top beam, there's going to be some sort of moment at the reaction, but it's going to go to 0 there, right at the end. Whereas for this one, there's going to be a reaction moment, and there's going to be a moment here as well, okay? So it's going to create a constant moment across the beam. So The deflections will look similar, but they won't be exactly the same. Okay. So they're not exactly the same thing. Good question. Okay, so Jeff has another very good question. So is this a simpler way of solving for deflection as opposed to finding the deflection equation from derivatives, at least for a moment? In a way, yes, right? So principle of virtual work is a way to solve for deflections in a little bit more direct way. The disadvantage of principle of virtual work is that you solve for deflections in a discrete way. So for every deflection that you want, you need to define a new virtual system. By doing the double integration method or some other analytical methods, what you do is you get an equation for the deflection, for the deflected shape. Okay, so that's what we're not doing in this class. We're avoiding it because those methods are a little bit, for what they give us, they tend to be overly complicated, right? Okay, generally we don't want an equation for the deflection. We generally just care about where the maximum deflection is occurring. And I strongly think that by just drawing a qualitative deflected shape and then kind of isolating the place where you think the maximum deflection is, or isolating a few places, you can then just use the method of virtual work to solve for those deflections, and you're okay, right? So I think it's a much more convenient approach than solving for the entire deflection. Okay, because it does get messy when you try to go from moments to deflection. Right, but if you really wanted to determine what the exact equation for the deflection is, then you'd have no choice but to use one of those methods from chapter 6 in the book. Okay, good question. All right, so that's external work. Okay, again, we don't really care. The point here is not necessarily the deflected shape itself. It's just simply that work done by a moment is equal to the moment times the angle of rotation at the point of the applied movement, and the work done by a force is the distance traveled by that force at that point. Okay. So now we shift over to the right side of the equation, right? The internal work will strain energy, okay? And for now, again, we're assuming the beam is in pure bending. So let's say we apply force P to a simply supported beam. That's going to cause our beam to deflect, right? As shown by the dashed line, okay? And so, right, in addition to that, it's going to cause internal moments to develop, right? Again, nothing new. We've solved for these, right? So you get a moment diagram for this beam. So there's internal moments developed by the applied force P. So we need to find what the overall work is done by that force. The external work is done by the force. We need to find out what the strain energy is in the beam due to that deflection, right? How much is it deforming, and what work are those internal moments doing throughout the length of the beam? All right, and to do that, we need to consider a infinitesimal sliver of this beam, which we'll call dx, okay? So if I zoom into dx over here, all right, I will see that internal moment MP, right, due to the stresses developed across the cross section of that infinitesimal element, is going to cause the face, the cross section, to rotate, like you see there, by an angle d theta. Okay. All right. Remember, stresses are linear from the, from the neutral axis. So they're 0 at the neutral axis, and wherever they're compressive, right, in this case at the top, they'll push the beam one way, and then when they're tensile, so the overall effect is that the beam rotates at that point. And that's what actually creates the curvature, right? So based on our definition for external work, we can kind of adapt that for internal work as well. So the work done by that small section dx would be dwi, and that is my internal moment at that section times the angle of that section, okay? And so all we need to do to find the strain energy or the internal work across the entire beam is simply sum all these infinitesimal elements together. And obviously when we're talking about infinitesimal elements, when I say sum, I really mean integrate, okay? So sum over entire beam. In other words, integrate. All right, so my total internal work is the integral from x equal to 0 to x equal to L, which is the length of the beam, of MP times delta theta. But we have an issue here, right? What's the issue? Can you calculate this integral? Right. So Noah's saying so x. So we have x for the bounds, right? And in fact, I should also emphasize that MP is a function of x, right? Because that's how we always get it. But then our integration constant is theta. So we need to replace that theta with something in terms of x. All right. But if you search your memory banks all the way back to module 4, I believe, when we talked about deflected shapes, you guys remember a relationship between theta and x? Kind of. This may be a hard question. So remember that I defined the derivative of the angle, right? When I was going through the relationship between shear, moment, angle, and deflection, I defined the derivative of the angle as the moment over EI, right? So that's one of the fundamental relationships here. So slope of the angle is equal to the moment over EI. Slope of the angle, does that make sense? Okay, so that's a fundamental relationship, and all I need to do is change this around so I can get it in terms of d theta. Okay, so this is a nice little relationship which we can then plug in right here, and so we get mpx squared over EI times dx, and we're good to go. Then we can solve. And so Jeff has a question. So EI becomes a constant when substituted into the integral. No, not necessarily. Okay, I'm just kind of assuming here that it's constant, and generally will be, but it can also be a function of x, right? And so can, yeah. E and I can be both functions of x, but that doesn't prevent you from solving the integral. All right, so a lot of equations. We got one more page of equations, and then we'll be done. All right, so we've got our definition for external work. We've got a definition for internal work when it comes to bending. So all we have left to do now is put it all together and define a principle of virtual work for a beam system, okay? This is pretty much same procedure as we did with trusses. That's what's really nice about virtual work, okay? So I'm giving you a very simple real system here. We have simply supported beam. We're applying a load P at the point C. We'd like to know what the downward deflection is, delta D, at point D, okay? It's always good to draw the deflected shape so you have a kind of a general idea of what you're looking for, okay? So we're looking for D, delta D. So what do you think we need to do in the virtual system? Okay, P equal to 1, apply a load at D, apply a virtual load at D, good. Some teamwork there, nice. Yeah, so we apply a virtual load at D, PV equal to 1, right there. And then we need to solve for, remember, virtual work again is real displacements or real deformations times virtual load. So we need to find what the internal virtual moments are in the virtual system, and then we need to find what the internal deformations are for the real system. But to do that, we need to essentially find the moments for both anyways. So we'll start with the real system. We'll cut a section here at S. And so if I cut that section, then I would get a system that looks like this. Yeah, I would have a reaction. I'm going to look to the left. So I get a reaction there at Y. This is point C, obviously. And then I get a shear. I'll call that SI. And I get an internal moment MI. Okay. So what's the first thing we can do here? I told you we weren't going to worry about shear, so we're not going to worry about it. Just ignore it. We can solve directly for the moment, right? We don't need to solve for shear if we're using kind of the equation method. So simply, we use this, we'll do a more concrete example in a second, but I'm just walking you through the procedure. So we find MI, and we ignore the shear, okay? So you find the internal moments of the real system. Then we go down to the virtual system, and we do the same thing, right? So we would get a virtual reaction here, and we would get a virtual shear and a virtual moment. Okay, again, and ignore the shear and just find, right? Okay, all that we know how to do, all right? And so the thing that's left is to define the equation for virtual work. And again, this is essentially a modified version of what we did for the truss, right? So we're not going to go through the whole derivation again. We're just going to draw an analogy to the truss system and use it here. So it's, again, external virtual work is equal to internal virtual work, right? Which means that our external virtual work in this case is being done by the load, it's done by the load PV over the displacement delta D, right? So virtual loads times real displacements. And our internal work is being done by the virtual moment over whatever the real deformations are in this beam, right? So whatever that rotation is. So I should define that here, right? So this is my d theta, okay? So it's going to be the integral from 0, let me move this up. Come on. So the integral from 0 to L of the internal moment, right, which is a function of x, times my d theta, okay? And again, we know that d theta is a function of the real moment here, just like internal deformations in the truss were a function of the real forces. And so I can modify this to okay, so notice that before here, I'll put a little note here, okay? Notice that the MP was squared because, well, let me write at the bottom here. I'll make a note here, okay? MP squared is because this is real work, okay? So we were just talking about the work done by completely by the real system. Because this is virtual work over here, then we have a virtual moment times a real moment. Just like before in the trusses, we had a virtual force times a real force, okay? So that's our definition for virtual work. All right. So this is just the same exact thing I just did, but in words, so you can follow it. So you're going to generally start with step 1 would be to draw the diagrams of the beam with the real loads and then the unit virtual loads. Okay. Always helpful here to draw the qualitative deflected shape. Right, that'll help you figure out what deflections you're really solving for. And for the unit virtual load, you need to decide what type of load to apply depending on what you're interested in. So if you're interested in external displacements, so a delta, you would use a virtual load, a virtual force. But if you're interested in a rotation, external rotation, then you would use a moment, okay? Then number 2 is to divide a beam into segments of continuous loading, okay? I didn't touch that here, but that's fairly easy to see. It may be in some cases that, I'll draw another little note here, okay? MIV or MI may be piecewise. right? Right? Especially if there's discontinuities like a load P here, right? That's going to create a discontinuity in the moment. And so you may have piecewise functions. That's okay. Just split the integral into different segments of continuous functions, and then you can sum them up at the end. So this is what this is saying, okay? So for both systems, make sure you use the same segments, right? And we'll show an example of it. And step 3 is the one where you calculate the internal moments for both cases. There's a little typo here I'm going to fix. So this should be MVI, and it should be MI to agree with what I just had here, right? Or MIV. And same thing here. Okay, so you solve for those internal moments, and then you use the principle of virtual work to calculate the deflection of slope, right? So if you chose PV up here, then you would use this equation. If you chose MV up here, you would use this equation. Okay, so a lot of words, but that's it. Okay, so that's the principle of virtual work. So we're gonna do, so that's it. All right, so we're gonna take a breath here, and then we're gonna do an example. Okay, so before we do an example, are there any lingering doubts? I know you guys are probably thinking, okay, I don't even know where to start, but it's actually not that bad once you get the hang of it. Okay, so we've got 20 minutes. Do we want to do breakout rooms, or do we want to just work? In the interest of time, let's just work through one example, and we'll do breakout rooms next time, next lecture. All right. So one thing I forgot to mention, which you saw in the next slide, is that sometimes these integrals can be substituted by using product integral formulas from the table in Appendix 2 in the book, which I've very conveniently included here. Okay, so this table actually gives you the products of some common integral, common moment shapes, and so you can kind of avoid doing the actual integration part. Okay, it may save you some time depending on if you're dealing with very complicated stuff. So we'll do an example of using these tables as well. All right. So let's do this example, example 1. Okay, and we may only get to part A, but that's okay. This is a simple cantilevered beam. The example is asking us to compute the displacement at A and the slope at B. So Kobe had a question. Same subject for the asynchronous lecture. So the asynchronous lecture will be on frames, virtual work for frames. And then the following synchronous lecture, we'll finish doing these examples on beams, and we'll do some examples on frames as well. Okay. So back to this problem. So we'll do part A will be just to focus on finding the displacement at point A here. All right. So I'm going to color code this to be easier to follow, but I'm essentially going to go through these steps. So step 1 will be in green, okay? And so step 1 is to define my real and virtual systems, which I've kind of done here already, and also draw the deflected shape so I get an idea, a better idea of what's going on. So I'm going to start by drawing the deflected shape. No, that's bad. You know, it's really hard to draw on a tablet. You do these by hand much better. Okay, that's about as good as it's going to get. All right, so that's my deflected shape, roughly. This is a right angle, obviously. And this is my delta A that I'm interested in solving for. And in the virtual system, I need to draw my load. So that's going to be at A, okay? So I'm going to apply, because I'm interested in delta, I'm going to apply a downward virtual load of 1. Okay, so that's step 1. We're done. All right, step 2. Make that red, okay? Step 2. Divide the beam into segments of continuous loading and EI, right? So EI may sometimes be discontinuous as well. In this case, we don't have to worry about that. So we just need to identify segments of continuous loading, right? So for the real system, the continuous loading is going to happen from B to the support, right? So essentially the entire beam. But for the virtual system, there's a discontinuity there at A. So I need to split that into sections. So I'm going to make a section 1 here and a section 2. This is step 2, by the way. But because I split it in the virtual system, I need to have an equal split in the real system as well. So I'll go ahead and define section 1 and a section 2 in my real system as well. All right. So that's step 2, pretty easy. Step 3, do that in purple. All right, so this is the hard part. For each segment, we need to write an equation for the internal moments in each one. All right, so I'll start with the real system, step 3. Okay, and I'll start with section 1. All right, so oops. So that's my beam, my load P. Distance X. And so I'm going to ignore the shear. I'm just going to worry about solving for the moment. That's going to be my moment 1 there. Okay. And if I set up my sum of moments, I'll do it around this point O here. I get Px plus M1 equal to 0. Thus, M1 equal to negative Px. Okay. For section 2, because there's not actually this continuity here in the real system, it's the same as section 1, right? So the drawing wouldn't change. So my equation stays the same. Okay. Still important to split it though, because we need to match the integrals for the real and the virtual system together. All right. So then we go over here to the virtual system. Let's draw our section 1. I'm going to copy this over. Sheet. I need to make a few changes. So my section 1 actually doesn't have the load there anymore. So it just looks like this. And so it should be fairly easy to see that. And I have to change this to M virtual 1, right? Change my moment because now it's virtual. But it should be fairly easy to see that that moment's equal to 0. Okay, and then I'm going to draw my section 2. There I need to apply the load at A. So that's my PV equal to 1. And in that case, my sum of moments is going to be equal to PV times L over 2 minus X plus MV2, right? To be careful when I copy paste. MV2. That's equal to 0. So I get sorry, flip that, didn't I? It should be X minus L over 2. And then here I get L minus L over 2 minus X, okay? Because that PV is equal to 1. All right, so those are my moment solutions. Any questions there? We're almost done. So that's my step 3. And then finally, step 4, we'll do in blue. Step 4 is use the principle of a virtual work expression. So in this case, because I applied a virtual force, I'll use this one. So step 4, principle of virtual work. PV times delta A is equal to the sum, to the integral from 0 to the end of my first section, right? So I'm integrating for the first section. So that would be MV1 times moment 1 over EI dx, right? So this is section 1 plus L over 2 to L MV2 times M2 over EI dx. That's my section 2. All right. And that's it. So then I just plug everything else in, solve, and get my delta A. So this is equal to MV1 is L over 2 minus X. I can take the EI to the outside because it's constant. This is negative px dx plus NV2 was 0, right? 0. So 0. Right. Doesn't really matter what that is because that's all 0. Okay. And so I just focus on this side. I can take the P out as well. I get Lx over 2 minus x squared dx.
Is there supposed to be a negative carried out with that P?
No, should be that, right? Yeah. Thank you. I mean, either way would work, but yeah, that's the way I had it in my notes. Okay, so 0 to L over 2. And if you evaluate all that, you get 5 over 48. That, okay? So when we divide out by the PV and we have delta A, doesn't really change anything. But I always like to be explicit about that because the units can change, right? So maybe just to be completely divided by 1. I don't have units, right? So I'll just say divided by PV. Okay. So it looks like I got some questions. I probably did do this quickly. And so I thought the other way around, MV1 was 0. Yeah, I think you're right. Yes, sorry. It's a nice thing about having the tablet. So that should have been MV1 here. And then, so I just flipped them. Thank you. But the overall result is the same. Oh, yeah. So that should have been L over 2 to L. And L over 2 to L. Correct. Yes. That look right? All right, so that's all we'll cover for today. The next two examples would be finishing this example and doing another example where we'll actually use the tables instead. But those we'll do interactively in the next Thursday's class. Okay, so I'll publish another video lecture on applying this, but to frames, which means that we also have to take into account axial deformations. They're essentially a mix of trusses and beams together. And then we'll do next Thursday will be finally a run through both beams and frames in terms of doing more examples. Okay. So I'll stick around for a few minutes, but other than that, thank you guys for sticking around, and I'll see you next week.
Excuse me?
Yep.
So for part